Here we go. Okay, so welcome everybody. So my name is Philipp Gerbert. I'm at Unternehmertum and would like to talk about quantum computing. And I called it, we have quantum supremacy. Now what? Referring to the famous experiment of Google from last year. Now, since quantum computing is obviously a slightly complicated subject, so I try to compress it in 10 to 15 minutes and open lots of aspects, and then you decide where you want to go into in the Q&A. I try to make it interesting from people who don't know what I'm talking about to experts, which will be a challenge. And perhaps in the end, I also comment quite a bit on what we're trying to do in the Minuk ecosystem. Okay, so let's go. So first, it's always a good time to start with the comics. So this is a Gerbert, famously from 2012, mark the date, who's asked how is a quantum computer going, and they said the project exists in a simultaneous state of being both totally successful and not even started yet. And the boss asked him, can I observe it? And he says, that's a tricky question. So if you have no clue what Gerbert is talking about, that will change over the course of this lecture, I hope, and in this presentation, and then we can deep dive into it. But he's actually referring to some of the most important aspects of quantum computing. It's a potential revolution, really, that mirrors a little bit the revolution we had in physics and quantum science, now into computation. Now let's start with a few statements, and then I'll explain them a little bit, okay? Now, first of all, 23rd of October 2019, famous Nature's paper, all the quantum world had it before and was waiting for it to be published, where Google announced it had reached quantum supremacy. Now, what is quantum supremacy? Quantum supremacy is if a quantum computer solves a problem that a classical computer can no longer solve in a practical amount of time. Now, perhaps a few comments on that. First of all, what was the problem? The problem was sampling a random quantum circuit. I doubt anybody of you has ever cared about sampling a random quantum circuit. It's actually a problem who is a little bit better than just simulating a quantum computer. And the only relevance is actually a well-defined mathematical problem. And Google proved it can solve it with a quantum computer in 200 seconds, 3 minutes, and claimed the classical computer would take 10,000 years. IBM, who really wasn't particularly amused that Google was first, prepared immediately a refutation, which it published one day before and said, no. In reality, it takes a classical computer 2.5 days. If we use Summit, the world's biggest supercomputer, which just, by the way, has 40,000 processors, 200 petaflops, and 200, so to say, petabytes, just to say, if you actually run that for 2.5 days, you could solve it as well. So he claimed was Google hasn't really reached quantum supremacy. Clearly, I mean, IBM is probably right. No one would ever try to run it, but it doesn't particularly matter. It's still, much slower, obviously, than what Google showed. And it's a little bit, let me give you an example of what this is. Google essentially said, I know I'm better than airplanes. I now build a rocket and I can go higher than any airplane. And they went up to 30,000 meters. And IBM said, oh, if I take all the power I have in the world, build the best plane, I can also go up to 30,000 meters. At that point, that's irrelevant because it's clear it has proved all the concepts. So it goes a few kilometers higher. And at one point, it's very clear if you have a rocket, you can go somewhere where no plane can go before. Now, is it now actually a proof of quantum supremacy? And there's essentially no way to really prove quantum supremacy because complexity theory isn't really solved. So it's very hard to prove that you can find no classical algorithm that can solve it. And clearly in a few, in 10 or 20 years, we can probably solve this problem with a quantum computer. However, it was an extremely significant thing. In particular, they proved two things. They first of all proved, until then, there was a significant question if you actually could build that scale of quantum computer. In particular from Israel, there was a guy called Jill Kalai who continuously questioned, would large-scale correlations destroy a computer? And that was for one and for good proof. They proved there are no large-scale correlations. The other thing is actually quite a fundamental result. I mean, there's, for those who care, there's the extended Church-Turing conjecture that says, you can essentially, whatever is computable, you can do on a classical computer or on a Turing machine, and that's clearly no longer true. A little bit like, from classical computing to quantum computing. Now, what comes next? Many people say, oh, wonderful, now we're all should invest in quantum. We have a Moore laws type of development. And the answer to that is both yes and no. In a certain sense, or I can say no to both, but the question is why no? Is it no, will we have more than Moore's law? And in a certain sense, we will have more than Moore's law because quantum computers actually have a double exponential. It's sometimes called Nevin's law after Hartmut Nevins, the German who leads the Google program. And the other answer, no, we will have less because we haven't yet converged on the dominant technology. We're in the vacuum tube age. So we proved it's possible, but we haven't discovered silicium yet. So, the question is, what will really be the best quantum computing? The other question is, will we actually solve any practical problems over the next 5 to 10 years, not in 10 to 20 years? And it's called the noisy intermediate state quantum. And the answer is most probably yes, but we cannot prove anything. It will be an experimental problem. And that's why everybody is working very hard right now to show, that this being an experimental problem is not bad. I mean, if you remember, we could prove nothing about neural networks, only negative results. And suddenly in 2012, they solved vision and language in artificial intelligence. So and it will come to the applications that it will go to. The other thing is, okay, do I now have to worry about cryptography, RSA cryptography, that is the encryption of the internet? And the reason people ask that, because quantum computing got the attention of all the secret services in the world in 1994, when Peter Shor proved with a quantum algorithm, you can crack cryptography. You can factor prime numbers, which is into prime numbers, and that would kill cryptography. This is true. However, the algorithm actually requires, it's such a sophisticated quantum computing that we will not be able to do that in the next 5 to 10 years. Eventually, cryptography will fall. And by the way, before cryptography falls, all of blockchain will collapse. So in case you're in blockchain, focus on applications that are relevant for the next 10 years. I wouldn't necessarily invest in quantum currency, in cryptocurrencies, if you want them to last for longer and you haven't made up your mind how to improve them. Okay, now I'll tell you quickly what quantum computing is, and then we go to some applications. So quantum computing, just so you know at least a little bit. So you talk about quantum bits. Quantum bits are like bits. Bits can just be 0, 1. Quantum bits can point into any direction. It's actually, you should imagine them as pointing into any direction on a sphere. That's a mathematical representation, but a rather good representation. So I have a much richer state. People always say, okay, the second thing is superposition. So sometimes you say, well, there can be simultaneously 0 and 1. That's kind of true, but a much better way to look at it is to say, look, they can point into any direction. If you then ask, is it 0 or 1? Okay, it's pointing somewhat up. It's probably 70% 1 and 30% 0, right? But it's well-defined state. It's just not 0 or 1. It's pointing in another direction. The most important aspect of quantum computing is if you have several states, they act as a group. They don't act like individual states, but act as a group. And that increases the information density dramatically. It actually becomes exponential in the number of qubits. So it grows with 2 to the number of qubits. Sometimes people say, okay, quantum computers compute everything in parallel. That's why they're so fast. And that's kind of the worst picture you can have, because they're not like parallel computers. They don't compute in parallel, they compute together. And that is actually quite substantial. It's very hard to imagine exponential, but let's just see, I have now 50 qubits. If you had 60 qubits, you have 10 qubits more. Now it's easy to remember, 2 to the power of 10 is 10 to the power of 3. So a quantum computer with 60 qubits would be 1,000 times more powerful. A quantum computer with 100 qubits would be 10 to the 15 times as powerful. So that's essentially the difference between having 1 bit and the most powerful computer today. So it increases very quickly. That's Nevin's double exponential law. Now, we won't get that so easily because there are a few hurdles on the way, but that's the promise. That's why people get excited. The problem with quantum computing, it's extremely error prone. So they make lots of errors. Normal computers don't make errors. 1 in the power of 20 hardware errors, and quantum computers do. And it's a pain because quantum states, you can isolate them completely, then they don't make errors, but unfortunately you want to calculate with them, so you can't isolate them completely. You have to manipulate them, and then they make errors. And the worst thing, correcting these errors is horrible. And that's a real problem with quantum mechanics because there are 2 theorems. A, you cannot measure it. So if you cannot measure it, the question is, how do you actually know you have an error? As soon as you measure it, you're done. You destroy your state, you get a measurement, you destroy your state. And you cannot copy a state, you cannot clone it. So for lots of time, people thought error correction might not work at all. They now have a way, but it could require 1,000 qubits to correct one. So it's very far away. Quantum error correction is just very far away. And the last problem is, when you actually want to read out what you calculated, essentially, if you know what it is, it's via interference. So it's not easy to read things in and out. And that makes quantum computing a bit complicated. Okay, good. Now I'll go fast to give you a very few overview of ecosystem applications and hardware. So ecosystem, and perhaps what I'm presenting now is based on the work I had with Frank Grüss, where we were at BCG. Frank is now at Google, and I am at Unternehmertum. So you see here a little bit what is the ecosystem. These are just the most important companies by now. We have another one where we have all the players in the world, but you see you essentially have the end-to-end providers. We take the stack from quantum hardware, systems, software, application services. Google, IBM, and Rigetti, they are the 3 players that are kind of on one superconducting part. And in China, it's Alibaba. There's Microsoft that is actually on the one player, and Canadian company called D-Wave. Then there are all kinds of players that play in some part, are emerging, and so the Honeywells of this world, the potential, Intel got in, et cetera, et cetera. And then you have pure software players, and then you have players that only play in a small part of the spectrum. One thing you see there, you don't see much of Europe, you see essentially nothing of Germany. The situation is the following. If you look at research, Asia, US, and Europe are on par on quotations. If you look at IP, the US is far ahead. Then comes China, and then comes Europe. If you look at companies, the US is totally dominant. Then there are a little bit things of over the world. China is in the play, Australia is in the play. There's hardly anything in Europe. There's still something in the UK. If you point out some of the relevant players in Europe, there's a center at Delft, as you see a QTech here next to Intel, which is Delft. You have in Zurich a QT, which is actually one in ion traps and so on. This is quite, actually in Zurich, in Innsbruck. You have in Finland a company, so to say, IQM, which actually also now comes to Munich and has, a major outlet in Munich. And you have in Karlsruhe HQS, Heisenberg Quantum Solutions. And that's obviously something we need to change. And we're working very hard to build up the quantum system in Munich, but that's one of the major challenges for quantum. For the applications, I'll be very brief. The most interesting is probably the third. These are the most interesting applications over the next years. Chemistry is best positioned. Chemistry is great because they know quantum and they know computing. So they are well prepared. And there are lots of catalysts that have about 50 atoms that would be absolutely fantastic for quantum computing. Some of these applications, these catalysts, are extremely important for climate change. The most famous one, FEMOCO, would allow you to do ammonium synthesis. And as you might know, this is one of the biggest emitters of CO2. So we would solve tremendous CO2 problems if we could do it. We know that bacteria can do it. We don't know how to do it. The other one that's perhaps very important is machine learning. That's why Google is in it, and that's a little bit further out the mix. And then there are logistics and scheduling. That's why all the players are in it. The good news here is there are lots of German and European players on the user side, the chemistry companies, the auto companies, and lots of other parts that are in the game right now. Bosch invested heavily in the Munich area. We have BMW, Volkswagen has its part in Munich. Airbus, if they survive, the current Corona, are heavily in it, and Google has a group in Munich, etc., etc. So I think from the user side, BMW also very important. You're in good shape. The last thing I need to mention is technologies. So those of you who are in the wave, you see, there are. I said before, we are still in the vacuum tube age. You haven't yet converged on a technology. Most of the players are in what we call superconducting technologies. Then there's trapped ion. These are the ripe ones. Then there's photonic, silicon spill, and topological. The important thing to notice is that the number of qubits is only one variable. How long they live, in particular, can you calculate with them well before they make a collapse with mistakes? That's called gate fidelity. How can you scale well? And several of the other parts. So the Google technology, all the superconducting technology is a quantum technology of first generation. So they have superconducting circuits. These are very big. So it's very hard to scale them. Google was fantastic. And Google is often quoted as having 53 qubits. They actually have 140 qubits because the connections between the qubits are also qubits, and they are just there to control and to make sure that they don't interact. So you already have now, for controlling them, these intermediate qubits. It's clear that there's an enormous challenge to scale that, and that's why people don't believe this will be the latest technology. Trapped ion, where we have our Innsbruck guys and so on, they have a good technology right now, but they don't have many qubits, so they're working very hard on getting more qubits. And then there are the second generation one, photonics, that is primarily pursued in the US and Canada, and silicon on spin, which is pursued in Australia. Australia is betting as a whole country on quantum. They missed silicon and chips, so they want to win in quantum. Michelle Simmons, one of the leading person, was the Australian of the Year 2018. This Friday is a huge presentation on how Australia is the roadmap in quantum computing. What you typically then have, if you want to measure how good these things are quantum volume, how many qubits are, and how many operations can you make before you collapse because of the errors. And that quantum volume is actually, things that everybody is fighting about. And, there's this Nevin's law, that QC performs exponential in quantum volume. In addition, there's D-wave, which is not qubit-based, so it's another part. And the last thing, quantum algorithms. Just to know, quantum algorithms is where there's a quantum zoo. There's about 100 major quantum algorithms that are listed by NIST. And all of those you typically hear of, like Shor's algorithm, HHL, and so on, all the classical algorithms that prove cryptography, they essentially, if you put them on the matrix, you can put them on the matrix, how much is the speed up, how good what problems can we solve with them, and how robust are they against errors. And all the classical, are on the right lower side. They're extremely sensitive to errors. We will not be able to do them for a very long time before we have quantum error correction. All the interesting ones are at the top left, the workhorses, the red thing is just collapsed. These are very interesting. That's what we'll have over the next year, but we cannot prove what their speed up. We don't know how well they will perform. That's why I said the next years are really an interesting area in experimental part. We will have to decide experimentally how we will perform, and we'll see how well they will perform, okay? I skip over the market projections because frankly, they're all hockey sticks. We just don't know. We have to wait when they come and just go to, so to say, the summary. So the summary is, obviously, Google's Quantum Supremacy publication was a major milestone. It proved that quantum computers will deliver interesting results. The next 5 years constitute the so-called NIST periods, noisy intermediate quantum scale. You can hardly prove anything, but they're experimentally extremely interesting. That's why everybody is putting money into that. Cryptography is not about to collapse. It's far away. However, it will eventually collapse. The current superconducting hardware dominates, and it will deliver very interesting results in the NISQ area, but it's still the vacuum tube age. We have extremely promising applications. I think the material science and climate change are the most interesting. And there's an almost infinite amount of algorithmic innovation. Actually, if you're a computer scientist, you can learn algorithms and quantum computing without knowing anything about physics. I just warn you, currently you learn wonderful gates. Whether gate-based algorithms are the ultimate answer, we do not know. You can just see how large the quantum volume would be to apply Shor. It's way bigger than the Google, the largest number you probably ever cared for. So that means that either the algorithm is extremely inefficient or Shor, the problem is really extremely hard even for a quantum computer. Okay. I ran a bit over time, so I stop here. I just wanted to say, if you have some publication, I gave some references. The important thing is perhaps as I showed before, we really have a problem in Munich. We have some very good people, but no one has yet united them, and we're not pulling the same direction. We now decided also jointly with the Technical University, we will build a quantum venture lab. We'll try to collaborate with the Push Quantum and try to coordinate people here in the Munich area in order to, we have lots of quantum potential, IQM is here, etc., but in order to really build something and join in this race. Thanks a lot.
All right, thank you so much, Philipp, for your insights. We already got a bunch of questions for you. Thank you very much also, guys. I think the new tool works really well for you. I'll just go by some that we thought that got a lot of likes recently. I think first of all, Philipp, first question that comes from the audience, are programs written differently for a quantum computer as opposed to a regular computer?
Yes, absolutely. So the standard way, most technologies I showed are so-called gate-based quantum computers. The one exception is D-Wave. So for that, you have quantum gates. So you do like in normal computing, you have standard gates, the NOT gate, for example, or the OR gate and so on. Quantum gates are a little bit special. They have to be invertible. So you can have, NOT is okay because NOT you can invert, but OR is not okay. So the most famous gate was actually the C-NOT gate, which was first published by Ignatius Sirac, who is actually in Munich, and Peter Zoller in 1995. Very, very famous, and they proved they can do that on an ion trap. But these gate-based computing, you can simply learn, and you can also learn, how you do Hamiltonian-based computing if you want to use D-Wave. All the major players, all the end-to-end players have a language out there, so you can do it a little bit higher level. You don't have to do machine level, so to say. They are all reasonably similar, so most good quantum computer scientists know all the major languages, Cirq or Qt and so on, by IBM, by Google, by Rigetti, etc.
Nice. Thank you, Philipp. The next one. Do you believe that Germany will ever be able to catch up to the tech market, especially when comparing German companies to global players such as Google or Amazon?
I do. Well, let's say there are two things that I think, first of all, Amazon is not in the game yet. Everyone is speculating about Amazon. Amazon and Apple are not in quantum computing. Amazon collaborates a little bit with IonQ. I think there is a good chance for actually catching up or contributing for two reasons. A, the US introduced an export control for quantum. That actually means that they cannot export quantum computers. It's a big problem for IBM, which kind of sold a quantum computer to Germany, how to do that. D-Wave can, so Jülich bought a D-Wave machine and so on. So IQM, a Finnish company, which was actually where the CEO is from Munich, you might know him, some of the people here, Jan Götz, and he also has, they will also come to Munich. They try to, be the European player, so to converge. There are lots of things you can contribute. You can contribute components, you can contribute software, and software Europe is not that bad. Also Germany is not bad. Jülich is quite good in technology, but hasn't done anything to transfer the technology. The biggest bottleneck right now is the venture capitalists are in here. Actually, several of the Munich venture capitalists are heavily invested in quantum. Bosch invested in in Zapata and in IonQ, etc., Bosch Venture Capital. The bottleneck right now is people actually going out and entrepreneurs and starting to build things like that. I mean, Jan, he joined IQM within, 1.5 years. He went from nowhere to being one of the most famous quantum computer scientists in Europe. So I think there's lots of opportunity. That's why we're trying to build the quantum labs. We have lots of basic technology here with lots of algorithmic know-how. The community is very well connected. There's no reason why we couldn't join the race.
Great. One other question that came up: how can or should startups and companies engage in quantum computing without doing fundamental research?
Collaborate. So what does Intel do? It collaborates with Delft. Microsoft hired its top quantum computers from Delft in Holland and from ETH at Zurich. You have labs. You need to collaborate. What you need, I mean, for superconducting quantum computing, I showed you the picture at the beginning of Sycamore. If you ever saw a superconducting quantum computing, they all look the same. You wonder, what are people doing differently? But what you see is just the cryogenic device. For superconducting, you need to cool it to 15 millikelvin. Just to know, someone once asked you, can't you do it in outer space? And the answer is no. Outer space is far too hot. Outer space is at 3 Kelvin. 15 millikelvin is really quite close to absolute zero. The interesting thing is it's actually a reasonably standard technology. So the leading company for cooling is actually in Finland. That's why you had IQM in Finland, so to say. We have great cryo technology here in Munich. So you can you can build cryo technology. You can build superconducting wires. You can build lots of components for the control. You can start in photonics. We have great quantum optics. You can start in algorithms. There's lots of realm of algorithmic innovation, and there's lots of parts of it. You can work with VW, you can work with BMW, you can work with Infineon. They all in the game of, so to say, collaborating, and they love to collaborate with young people. And so that's why we're starting this quantum venture lab, because we think it's actually an enormous opportunity in quantum tech in general and in quantum computing specifically.
All right, thanks. The next question, 8 likes. What role does China play in this technological race? I imagine that they identified this as a promising topic.
They do? It's interesting. So quantum tech has 3 parts. One is quantum sensing, which is primarily used for navigation of satellites. They're all the triads are good. It's not such a huge market. It's a very good market. The second is quantum communication. Quantum communication means you encrypt communication via quantum. So in a certain sense, you can break the standard quantum, the standard encryption via quantum, but you can, the poison is also the medicine, so you can encrypt it via quantum. In quantum communication, China leads. It sent the very first video message via satellite 2 years ago, actually to Vienna. It's a guy who studied in Vienna with Anton Seiler. And they built now a whole quantum network, and they are far ahead. In quantum computing, they're far behind. Alibaba is the most important. There's Hebei University, and there's Alibaba as a company. But it's clear that's also why the US is currently so restrictive with export controls, because that's one area where China is behind. If you compare it, I mean, I would rate Australia far ahead of China at this point in time in quantum computing.
Nice. Next one. How would you search for use cases within a company that does not necessarily engage in solving problems that require high performance computing or the like?
Okay. What can I say? It's a little bit, why would you buy a rocket if you don't want to go into space, right? Primarily, quantum computing is a high-performance computing methodology. However, there are some general things. For example, what does VW use it? VW had a quantum bus at Web Summit in Lisbon, and they did a navigation system where with quantum, they would actually predict the traffic. So not just say, you know, where to go now, but I predict what traffic there will be. It was still a game, but still they do something. There are people who do fluid mechanics. That's why Airbus was in it, etc. So you can do all kind of logistic problems. Still, you cannot solve them as well. The core companies are really chemistry companies, so the BASFs and the Bayers of this world who say, okay, I can build a better need a catalyst for better solar cells, for better ammonium, for better storage devices, and so on. That's one. The other interesting part is machine learning. Machine learning is very weird because I told you quantum will make it exponentially faster. And most people think, okay, instead of linear, I have an exponential speed. In machine learning, it does something different. Machine learning is primarily linear. Today, you know, it's primarily matrix multiplication, but quantum can do it in logarithmic time. So going from linear to logarithmic is also an exponential speed up. However, you actually have to read in the data and read out the data. And that's a linear problem. It's called the quantum memory problem. So in machine learning, we know precisely how we would speed up machine learning, but we don't know how to get the data in and how to get the data out. That's a very interesting problem. Obviously, machine learning is something of very wide application. But for most companies, it's really most interesting if you have high performance computing, but you lose high performance computing for a lot if you can do it. You can simulate chemistry, you can do better, you know, fluid dynamics, which is you can build better cars, better planes, whatever you want to do. You can do better algorithms in the financial market. You can, you know, you name it. I mean, if you solve hard computational problems, they have quite a few applications.
Nice. Thank you, Philip. I think we have one last question that we would like to ask. And this one is, how can you ensure cybersecurity in the era of quantum computing?
Okay, there are two ways. One is you do quantum encryption. As I told you, the poison is also the medicine. You can use quantum communication and you exchange a quantum key. That's what the Chinese are doing. And they're building a quantum network. We will also build, KPN will also build a quantum network. And you can exchange, so the reason you can do it, because if you exchange an information in a quantum form, if someone listens, he destroys the information. So you know that he listened and he cannot, you know, he cannot decrypt it. So that's very nice. Unfortunately, it's very expensive. So it's a great thing for governments and secret services. It's a great thing for financial services and banks, but it's not something for you and me. The other thing is you can find an algorithm that cannot be cracked by quantum. I didn't tell you, I mean, how Shor algorithms cracks quantum, but essentially it uses a hidden symmetry. And it's a weird, you know, mathematical thing. I don't want to go into it, but there are, you know, it can solve elliptic stuff, so it can solve all the cryptocurrencies, identification, etc. But the NIST, the Institute of Standards in the US, and actually the Paderborn Institute, they have tons of algorithms that they think will be very hard to crack by a quantum computer. The trouble is, we tried to crack factorization for 40 years, so we know how hard it is. It's almost impossible to prove that something is hard to crack. So the standard organizations are working as hard as they can to agree on something where to move to. Because there's been all these things, you know, where do you think it's safe enough that you move? What people then do is large banks, I know several large banks who are preparing for that because they say if cryptography falls in 50 years, we have to start preparing now. Now, what is the preparations? A little bit like the year 2000. The preparations, they just say, they prepare all their systems so with one switch, they can change encryption. Today, no one prepared a system to change encryption, right? I mean, it's just not something you think about. But agreeing on this is something that the standard institutes are working very heavily right now, and will get some proposals in the next 3 years, and then let's see what we agree upon. Whether that will hold or not, we don't know, but frankly, no one knows why factorization holds, right? I mean, no one could know 40 years ago that factorization would hold up so long, right? So it's it's something where we have to feel reasonably comfortable, or you go all the way to quantum encryption.
All right. Thank you very much.
That's just one. Excuse me, just one. The difficulty with blockchains, just so you know, because I know lots of people love blockchains. The difficulty with blockchains is that lots of blockchains, you cannot change the blockchain. That's the biggest weakness of blockchain. You launched a blockchain and the governance is so difficult often. I mean, unless you have a central government, but you don't want a central government. So as soon as you launched it, you cannot change. So if you cannot change it, you're totally exposed to someone cracking it, right? And so whenever you think of blockchain applications, always think, okay, if something happens, can I change my encryption? Do I have any governance that I can switch that? Otherwise, you're at full risk.